Today let us discuss the electronic transitions. Suppose let us take an object like this, and what is the color of this object? This object is having the green color, and why it is having the green color? Suppose we are going to irradiate this object with the visible light, and this visible radiation is going to fall on this object with intensity of radiation I0. Then this object will absorb some of the radiation, and the remaining radiation is coming out of this object as IT, where IT is the intensity of the transmitter light. Now this transmitter light can fall on the eye so that we can perceive the color of the object as the green color. But actually whatever the radiation that is coming to the eye is not the radiation corresponding to the green color, but it is the complementary color of the green color. That means here the object is going to absorb some radiation, and the remaining radiation is a complementary radiation to the green color. But here the question is how this object can appear as a green color. The object is going to appear as a green color because it is going to absorb the visible radiation. So what happens to this absorbed radiation? This absorbed radiation is used to produce the electronic transients within the molecules. So if any object is colored and absorbs the radiation, it is mainly due to the electronic transients. So in order to understand the electronic transients, let us take the case of sodium. Sodium is having an electronic configuration of 1s2, 2s2, 2p6 and 3s1. And suppose if we put the sodium in the flame, it gives a golden yellow color. Why it is going to give the golden yellow color? So if we see the electronic distribution within the sodium, within the first shell, 1s orbital is present with 2 electrons, and in the second shell, 2s as well as 2p orbitals are present with 2 and 6 electrons, and the outer shell is the third shell where the 3s orbital is present with 1 electron. And we can also observe a 3p orbital within the outer shell which is vacant without any electrons. Now when we supply the energy, for example we are going to supply the heat energy, then this energy can be absorbed by this sodium so that the electron in the 3s orbital can jump to the 3p orbital. Since the 3p orbital is more energetic than the 3s orbital, the electronic transition here requires energy. So now the sodium can absorb the energy so that the electron is jumped from the 3s orbital to the 3p orbital. But this state is an excited state which is not stable, and when this electron is again coming back from the 3p orbital to the 3s orbital, it will release the electromagnetic radiation. So this electromagnetic radiation we can observe as an yellow color when the sodium is going to be placed in the flame. So in this way, electronic transitions are responsible for both absorption as well as excitation. So this is the case of atoms, but when we are coming to the molecules, the situation is not that much simple because the atoms involve the chemical bonds. Now let us see what happens in the molecules. Let us take a molecule like this having 3 atoms, and here the central atom is attached with the 2 other atoms, and here the bonds between these atoms are not that much fixed and they can behave like springs so that their bond length may be either increased or decreased. When we irradiate this molecule with the electromagnetic radiation, this can bring few of the transitions in the molecules. So one of the transitions is the electronic transitions, where the electron can jump from low energy state to the higher energy state. And second type of transitions are the vibrational transitions. As the chemical bonds are not fixed and they are highly flexible, when the electromagnetic radiation is going to fall on this molecule, the bond length may be either increased or decreased. And even the bond angles may be modified so that the atoms in the molecule can be vibrated, leading to the vibrational transitions. And finally, we can also observe the rotational transitions. When the electromagnetic radiation is very less energetic, then it can produce a simple transitions on the electrons so that the electrons can be rotated either clockwise or anti-clockwise. In this way, whenever a electromagnetic radiation is going to fall on the molecule, it can produce 3 types of transitions: electronic, vibrational and rotational transitions. Among these, electronic transitions requires high energy and rotational transitions requires less energy. So whenever the electromagnetic radiation is going to fall on the molecule will try to undergo electronic transitions. So many of the objects are colored because of these electronic transitions. Now in this video we will focus on the electronic transitions, what are the different types of electronic transitions, how they are going to be formed, and what is the energy required for these types of transitions. Electronic transitions in the molecules. Let us take one structure like this, and this is the ethane. Which type of electrons are present within the ethane? You can see that ethane is having the carbon and hydrogen, and here both of these carbons are attached with the hydrogen. The bond between the carbon and hydrogen is the sigma bond, as well as between the carbon and carbon is again sigma bond. So ethane is mainly having the sigma electrons, so ethane can undergo a sigma to sigma transition. So here sigma is the bonding molecular orbital and sigma asterisk is the anti-bonding molecular orbital. Otherwise sigma is the ground state and sigma asterisk is the excited state. We can also call it as sigma as the HOMO, that is high energy occupied molecular orbital, and sigma asterisk as the LUMO, low energy unoccupied molecular orbital. So ethane, when we supply the energy, it can undergo sigma to sigma transition. Now let us take the case of another structure. This is the ethanol. Now again in the ethanol we can observe the sigma bond between the carbon and carbon as well as between the carbon and hydrogen, and we can also observe a sigma bond between carbon and oxygen. Apart from these sigma bonds, we can observe n electrons. N electrons are the non-bonding electrons or lone pair of electrons which are not involved in the chemical bonding, and they are present in the heteroatoms like the oxygen, nitrogen, sulfur, like that. Now which type of transitions are possible in the ethanol? Here we can observe two types of transitions, sigma to sigma transition and n to sigma transition. And here you have to remember that for n electrons there is no excited state or no anti-bonding molecular orbital because n indicates they are non-bonding. So since they are not involved in the bonding, there is no anti-bonding molecular orbital present for the n electrons. So here two types of transitions are sigma to sigma transition and n to sigma transition. Now let us take the case of acetaldehyde. Which type of electrons are present on the acetaldehyde? Again we can observe the sigma electrons between carbon and carbon as well as carbon and hydrogen, and we can also observe a sigma bond between the carbon and oxygen, and now we can observe a pi bond between the carbon and oxygen because the aldehyde is having the carbonyl functional group. And apart from these we can also observe the n electrons on the oxygen. So acetaldehyde is having all types of electrons like the sigma electrons, pi electrons and n electrons. So which type of transitions are possible in the acetaldehyde? So since it is having three types of electrons and we can have two types of anti-bonding molecular orbitals like the sigma anti-bonding as well as pi anti-bonding, we can have totally 6 types of transitions. Sigma to sigma transition, sigma to pi transition, similarly pi to pi transition and pi to sigma transition, and finally n to pi transition and n to sigma transition. So theoretically 6 types of transitions are possible for a molecule having all types of electrons like the sigma electrons, pi electrons and n electrons. But all these transitions are not practically possible, and within the spectroscopy the transition like the sigma to pi transition as well as pi to sigma transition are forbidden. That means they are not allowed, and we can observe only 4 types of transitions like the sigma to sigma, pi to pi, n to pi and n to sigma. These 4 types of transitions are only possible within the spectroscopy. Now let us go one by one with each type of transition, how they are going to be formed, which type of molecules can produce these 4 types of transitions. Let us start with the sigma to sigma transition. Which type of molecules mainly show the sigma to sigma transition? Because all the molecules are having the chemical bonds which are nothing but the sigma bonds, they will definitely have sigma electrons, so they will undergo sigma to sigma transition. But here our question is that which type of molecules mainly show sigma to sigma transition? So for example, let us take the case of cyclohexane. Cyclohexane is having the only sigma electrons, so it will only give the sigma to sigma transition. Similarly, alkanes like the propane. Propane is also having sigma electrons, so again it gives the sigma to sigma transition. So alkanes and cycloalkanes can only show sigma to sigma transition. These type of transitions are going to fall within the region of less than 200 nanometer, which is called the vacuum UV region. So these compounds like the cyclohexane can be used as a solvents because they are going to absorb the radiation within the vacuum UV region. Vacuum UV region is the less than 200 nanometer, UV visible region is the 200 to 800 nanometer. So when this compound is going to absorb less than 200, it will not interfere with the study, so it can be used as a solvent in the UV visible spectroscopy. So cyclohexane can be used as a solvent within the UV visible spectroscopy. Now let us go with the second type of transition, pi to pi transition. Again, which type of molecules mainly show pi to pi transition? In order to show the pi to pi transition, a molecule should have pi electron. So which type of molecules mainly having pi electrons? So let us take the case like alkenes like ethene, which is having mainly sigma electrons as well as pi electrons. So apart from sigma to sigma transition, it mainly shows pi to pi transition. Similarly, 1,3-butadiene, which is having the 2 pi bonds, and benzene, which is having the 3 pi bonds, and some of these conjugated polyene systems which are having the multiple pi bonds. All these can undergo pi to pi transition. And these pi to pi transitions are mainly responsible for absorption of the radiation within the UV visible region, with the exception of ethene, which is having the lambda max of 175 nanometer. All these transitions are going to fall above 200 nanometer. That's why these types of conjugated systems are responsible for the absorption of the color within the visible region. So here the compounds which are undergoing the pi to pi transition will mainly act as chromophores. Chromophores are the groups which are responsible for the absorption of the radiation within the UV visible region. And extended conjugation always produce a bathochromic shift, thereby they increase the capacity of the chromophore. Now let us see how this pi to pi transition is going to be produced. In the previous video already we have discussed this. So whenever a pi bond is going to be formed, it can form one of the orientation like this, where the positive and negative lobes are aligned above and below the plane, so that they form a highly stable molecular orbital. So this molecular orbital can be called as pi bonding molecular orbital. And pi bond can also be formed in another way, where the positive lobe is going to interact with the negative lobe of the another p orbital, which is highly energetic and less stable. So this can be called as pi anti-bonding molecular orbital. And again, when we supply the energy, electrons can jump from the pi to the pi anti-bonding molecular orbital, so that they will show pi to pi transition. Now let us see the third type of transition, N2 sigma transition. In order to show N2 sigma transition, the molecule should have N electrons as well as sigma electrons. So which type of molecules are having N electrons? For example, let us take the ethanol. Ethanol is having the sigma electrons as well as N electrons, so it can show N2 sigma transition along with the sigma to sigma transition. Similarly, the amines like the ethanamine again can show the N2 sigma transition, and ethers can also show the N2 sigma transition. So if any molecule is having an heteroatom attached with a single bond, it can show the N2 sigma transition. Again, these transitions requires high energy and they are going to fall within the region of less than 200 nanometer. So the compounds showing N2 sigma transition can also be used as solvents in the UV visible spectroscopy. So N2 sigma transition is going to fall within the region of less than 200 nanometer, but sometimes these compounds can show the end absorption, where they can absorb around 205 nanometer, 210 nanometer, and we have to select a solvent based on its end absorption. And fourth type of transition is the N2 pi transition. So in order to show a N2 pi transition, the molecule should have N electrons as well as pi electrons. So compounds like acetaldehyde, now the acetaldehyde is having all types of electrons like the sigma, pi and N electrons, so it can show the N2 pi transition. Similarly, the acetic acid again having the pi electrons and N electrons. Similarly, acetonitrile. So in this way, all the carbonyl compounds like aldehydes, ketones, acids, acid derivatives can show the N2 pi transition. But when the molecule shows the N2 pi transition, they can also undergo pi to pi transition. So N2 pi transition is observed along with the pi to pi transition in these molecules. Now let us see which transition requires more energy. In order to study this, we have to see the energy diagram of the different types of molecular orbitals. So sigma bonding molecular orbitals are more stable, so they are less energetic. Then we can see the pi bonding molecular orbitals, and then the n electrons which are non-bonding. And now if we see the anti-bonding molecular orbital, the pi anti-bonding molecular orbitals are somewhat less stable, and then the sigma anti-bonding molecular orbitals are very less stable, so they occupy the top position within the energy diagram. So we can observe the different types of electron transitions between these bonding and anti-bonding molecular orbitals. So we can observe the sigma to sigma transition, or pi to pi transition, or n to sigma transition, and n to pi transition. So in this way we have 4 types of electronic transitions possible in the molecules. But which transition requires more energy? The energy required for a transition depends on the energy gap between the two states. We can easily observe that the sigma to sigma transition is having the more energy gap, so it requires the highest energy. Similarly, n to pi transition is having the less gap, so it requires the less energy. Now if we see the energy order of transitions, we can arrange the transitions in the high energy to the low energy. So already we have discussed the sigma to sigma transition requires highest energy, then n to sigma transition, then pi to pi transition, and finally n to pi transition. And particularly sigma to sigma and n to sigma transitions requires highest energies, so they are going to fall within the vacuum UV region and they will absorb in the region less than 200 nanometer. Similarly, pi to pi and n to pi are mainly responsible for the absorption within the UV visible region, so they are going to absorb within the region of above 200 nanometer. So above 200 means 200 to 800, which is the UV visible region. Now if we take a molecule like ethanol, which type of transitions are possible in the ethanol? Since it is having the sigma electrons and n electrons, it can show sigma to sigma transition and n to sigma transition, and because both of these transitions are going to fall within the vacuum UV region, so ethanol can absorb less than 200 nanometer. Similarly, if you take another compound like the acetaldehyde, in the acetaldehyde we can observe all types of electrons, so it can undergo all types of transitions. Along with the sigma to sigma and n to sigma, it can also undergo pi to pi and n to pi transitions. So acetaldehyde will absorb within a region of above 200 nanometer because it shows the pi to pi as well as n to pi transitions. In this way, molecules can show 4 types of electronic transitions: sigma to sigma, n to sigma, pi to pi, and n to pi. The first 2 transitions are going to fall within the vacuum UV region, and the last 2 transitions are going to fall within the UV visible region. So that's for today. If you like this video, please subscribe to our channel, click the bell icon, and share this video with your friends, which encourages us to create more interesting videos. Thank you for watching this video.